Hello everybody and welcome. Today I'm going to show you how to implement regression analysis with Google Earth Engine, and we will start with the simplest methods. It is available in Google Earth's Engine, which is Linear Fit. Earth's Engine has several methods for performing linear regression using the reducers which are listed here, namely Linear Fit, Linear Regression, a Robust Linear Regression, and Reach Regression. We will start with the simplest method, which is a linear fit, and it computes at least squares. Zero estimate of a linear function of vulnerable is a constant term for more flexible options. 50. You can further then experiment with linear regression, robust linear regression, and reach regression, and you can read their implementation and their references for this method. So now I'm actually on the Guide to Google Earth Engine Guides webpage, which summarizes this linear regression options that are available in Earth's ancient well. We will start with the image collection, and I'm going to show you how to implement this on image collection. So how to do linear regression? Always image collection, because this is basically the most common type of problem that we need to and usually implement in other softwares. So we will start with a case of ANDV. So let's imagine we have an individual images over the whole globe. In this case, we are going to work with images available for the whole globe, and we would like to compute a linear regression over and divide to see and to retrieve the slopes, to see where the slopes of linear regression are positive or negative y is needed. Why do we need this? Usually, this is the linear trend of ANDV is used as a proxy for vegetation decline. And vegetation increase, which show in the positive or negative trends in vegetation. And that could be, for example, used as a proxy for land degradation, as a proxy for drought analysis, for the areas which experienced negative vegetation trend, and for positive vegetation transits, vice versa. It usually shows the vegetation recovery, which is also sometimes useful information to know. Of course, it's not as simple as it is. Usually vegetation is a function of not only it's a function of temperature, precipitation, soils, and also management. So it's not only depends on itself, but of course, when we run regression analysis over vegetation, then I'm serious. This is a kind of overall proxy of what is going on with vegetation. For this analysis, we are going to use modest images, which are available since 2000. So first, what we need to do is to basically add a band containing image data as the year since 2000. And since 2000 is because we are going to work with more this collection, which are available for the globe with a spatial resolution of 1 kilometer. If you just type here in ANDV, there are different options that are available, and this is a product that I'm working here. Modest Terra vegetation indices with global coverage and 1 kilometer resolution. If you click on it, you can see some details and availability you see from 2000. 90 dataset is available. And if you go to bands here, we can see what kind of bands are there. And I'm going to work with API and hence vegetation index. But you can also work with Dubai, for instance, if you choose imported New Zealand collection snips that will be imported to your Google or St. John. But I did all right as this. So here is basically a reliable collection that I declare the arrival of much more. This collection, the time important to Google Earth St. John, and I'm selecting here, and hence vegetation index. And here further, I apply a function that I have defined here, and I'm going to come back to it now. So the function is called createTimeBand. And here this function, I'm actually declaring a new function, where I'm basically adding a band containing an image data as years since 2000, so dependent on what kind of image collection you are going to work further, you should adjust this. So some images are available from 2000. Another quote from 1992. If you are working to preserve which are so, you should a this. And why do we need this too? 2 steps for a linear fit function is because linear fit requires a bent set of 2 band input image, where the first band is independent variable and the second band is a dependent variable. The following example will show how to do this. So because we need this to band image datasets, we create this in this regard. So what we do with this function, we call this function createTimeBand, and we declare a variable here where we get our image data from system time, which gets a year, and subtract 2000 to get this numerical values of the image dates, and it returns as function return image, which shows a year's linear regression to the collection variable that we have declared. And finally, map the collection to our cameras here in Google Earth Engine. So here what we have to specify, because when we identify where we are headed into outputs, then of this linear regression analysis are to bend match, which shows the scale, which is basically slope of your linear regression in other words, and offset is an intercept of a linear regression. And since here we are using a 3-band visualization, you have 2 shows a minimum and maximum values of this 3-band. So for a forward, we are going to use slope for green. We are going to use intercept, and for blue band again, slope. So here we are, going to use the maximum and minimum values that do have to decline in beforehand. How to do this? You can. After you run your analysis, you can use Inspector and identify the range of the slope and for your study area and intercept and make it more precise. Or you can also then use visualization function here. But this is already a second step. Let's just run this analysis. So this is basically the result of what we can see here is mapped. Slope intercept over of normalized difference, vegetation index, time series, PR. Zero mode is a special resolution of 1 kilometer for the whole globe. So is it? Visualization, of course, is not optimal, so here you should work with this and a little bit adjusted for your study area. So when I know, for example, this area here in Central Asia, in Uzbekistan, I know that there is a river going down, and of course the negative slopes are in red, because this is of water. This is a rewrite. If you click here, you could see as a values of your scale what it shows, the values of your offset, and you could adjust this to basically do your visualization. You can also use here as options directly to play with that 3-band visualization of unbent, visualization of its adjusted scales to make your study area more pronounced, and the results of your linear regression more pronounced. I did this for a layer and nose-add-layer. For another visualization was another function mapping layer where I just input image visualization parameters of 1 band where I don't use slope. Intercept, slope does algebra's elevation, but I only what I'm doing here. I'm on the visualization, visualizing the slope for my study area, and basically all of Ryson, which is shown in blue. I can open it for you, you can see that, and all negative slopes are shown in red. Neutral slopes are shown in yellow, and positive slopes are shown in blue. And that basically makes much more sense for me because what they can see the most positive changes were observed in highly educated, very intensively managed agricultural croplands. While on the periphery at the outskirts of the irrigated systems, we can see negative trends as a result of an ongoing land degradation and abandonment. While overall in the area of the desert, which is here, we can observe no trend, which is also now like zero slobs. So no changes, no trend. And if you go a little bit further up to the Aral Sea, you could see hotspots of negative trend of land degradation is an ongoing land abundant isn't gone. So basically, that's what I also was expecting to do. So as you can see, the code itself is rather simple. The visualization is not so good. It's not difficult, but you should invest some time in finding a better visualization. And for your own study area, and you can do it by working with a high visualization visualization parameters, sensor layer DAB, as well as use and inspect option in Google Earth Engine 1. Once you are clear about how linear regression fit works, you can also try out more sophisticated, the more complex methods such as linear regression or Bosnia regression, where you can also compute slopes and intercept of a linear regression, but that you were slightly more sophisticated algorithms to compute linear regression. So the task for you would be to apply this method for your own study area and to do visualization, so it makes sense that you feel good about it, and to interpret the negative and positive slobs of individual for your study area.